A century ago, the great polar explorers were pushing further and further towards the coldest places on Earth, the North and South Poles. The competition to reach these goals was matched by a less publicized but equally daunting scientific endeavor, the attempt to reach the coldest point in the universe, absolute zero. This mysterious barrier was a physical paradox as tantalizing as the speed limit of light, which can also never be exceeded. It was a frontier so enticing that rival physicists from all over Europe began a race towards this absolute limit of cold. This is a story of showmanship, setbacks, rivalry, and despair. The stakes were high. For the winner, there was glory and the chance of a Nobel Prize. For the loser, the prospect of being a forgotten foot soldier of science. When explorers ventured into the Antarctic, they experienced some of the coldest temperatures on Earth, reaching down to -80 degrees centigrade. But this was nothing compared to the ultimate limit of temperature, absolute zero, at around -273 degrees. Only in a laboratory, by liquefying gases, could adventurers take the first steps towards this holy grail, a place utterly drained of all thermal energy. Among the frontrunners in the race towards absolute zero was James Dewar, a professor at the Royal Institution in London.
It will be the greatest achievement of
In
our
1891, he gave one of his celebrated Friday night public lectures on the wonders of the supercold to celebrate the centenary of his great predecessor, Michael Faraday.
The descent to a temperature within 5 degrees of zero would open up new vistas of scientific inquiry, which would add immensely to our knowledge of the properties of matter.
James Dewar is a canny and I think very ambitious, practically minded Scottish scientist. He could really show both his colleagues and the fee-paying audiences who came to his immensely successful, brilliantly engineered lectures some of the secrets of nature.
Take this rubber ball. It bounces well, I think you'll agree. But let's see what happens after a few seconds immersion in liquid oxygen.
Dewar invented the vacuum flask to carry out his research, and it is still called a Dewar to this day.
Now, let's see what happens.
This phantasmagoric aspect of science always helped science to be accepted by the public. Though it is a little mystifying, it did play a role of having society, having the public accept that these weird people in the laboratories are doing truly interesting, if not magical things.
James Dewar's life was defined by the cold. As a boy, he used to skate on a frozen pond in Scotland. He claimed in later life that his most formative early experience resulted from an accident on the ice.
After Dewar fell through the ice, he was rescued But when he got home, they discovered that he had rheumatic fever, which put him in bed for 8 months. And he was in danger of having his limbs atrophy through palsy. And so the village joiner set him task to develop his limbs, especially his hand. And one of the tasks was to make a violin. And he developed a great deal of mechanical aptitude, which stood him in very good stead in later years when he had to create apparatus for his use.
Dewar's dream was to take on the mantle of the Royal Institution's greatest scientist, Michael Faraday. "70 years earlier, Faraday had done experiments showing that under pressure, gases like chlorine and ammonia liquefy, and as these liquids evaporate, their temperature drops dramatically. Faraday was curious to see if this method of pressurizing gases into liquids could be used for all gases. But some gases, what he called the permanent gases, would not liquefy, no matter how much pressure he applied, so he abandoned this line of research.
Faraday's was a mind full of subtle powers, of divination into nature's secrets. And although unable to liquefy the permanent gases, he expressed faith in the potentialities of experimental inquiry. The lowest point of temperature attained by Faraday was minus 130 degrees centigrade.
For over 30 years, no one could reach a lower temperature than minus 130 degrees. Absolute zero remained an elusive and very distant goal.
Now, Michael Faraday, in the early to mid-19th century, had left a kind of forlorn frontier for physicists and chemists, what he called the permanent gases, hydrogen, nitrogen, oxygen, which no means whatsoever seemed to be able to liquefy. And this was a kind of no man's land which one could not cross. And that was a standing challenge for the scientists of the later 19th century. It must be possible to turn these gases into pure liquids.
It was not until 1873 that a Dutch theoretical physicist, van der Waals, finally explained why these gases were not liquefying. By estimating the size of molecules and the forces between them, he showed that to liquefy these gases using pressure, they each had to be cooled below a critical temperature. At last, he had shown the way to liquefy the so-called permanent gases. Oxygen was first, and then nitrogen, reaching a new low temperature of almost minus 200 degrees centigrade.
Only the last of the permanent gases remains to be liquefied. Hydrogen, in the vicinity of minus 250 degrees centigrade. It will be the greatest achievement of our age, a triumph of science.
Dewar was determined to be the first to ascend what he called Mount Hydrogen, but he was not alone. The competitor Dewar feared most was a brilliant Dutchman, Heike Kamerlingh-Onnes.
Kamerlingh-Onnes was younger than Dewar, and to a certain extent looked up to the Scotsman as his senior. Dewar didn't have the same, if you'll pardon the expression, warm feelings towards his rival in the race for gold.
Dewar recognized that Kamerlingh-Onnes had a new radical approach to science and was planning an industrial-scale lab.
When Onnes took over the physics laboratory in Leiden, he was only 29 years old. And, well, he gave his inaugural address here in this lecture room, the big lecture room of the Academy building of Leiden University, and it was all there. He was explaining what to do in the next years, and he was talking about liquefying gases, making Dutch physics famous abroad, and, well, it was amazing how far-sighted all those visions were.
Kamerlingh Onnes's lab was more like a factory. He recruited instrument makers, glass blowers, and a cadre of young assistants who became known as Blue Boys because of their blue lab coats. Later, he set up a technical training school, which still exists to this day. Dewar and Onnes could not have been more different. Dewar was very secretive about his work, hiding crucial bits of apparatus from public view before his lectures. Onnes, on the other hand, openly shared his lab's steady progress in a monthly journal. Onnes was the tortoise to Dewar's hare.
In the case of Dewar, you had a brilliant experimenter, a person who could actually build the instruments himself, and a person who really believed in the brute force approach, and that is, have your instruments, set up your experiment, and try as hard as you can, and then you'll get the results you want to get. In the case of Kamerlingh Onnes, you have a totally different approach. He is the beginning of what later on was known as big science.
Unlike Dewar, Onnes thought detailed calculations based on theory were vital before embarking on experiments. He was a disciple and close friend of van der Waals, whose theory had helped solve the problem of liquefying permanent gases. Though their approaches were different, Kamerlingh Onnes and Dewar used a similar process in their attempts to liquefy hydrogen. Their idea was to go step by step down a cascade using a series of different gases that liquefy at lower and lower temperatures. By applying pressure on the first gas and releasing it into a cooling coil submerged in a coolant, it liquefies. When this liquefied gas enters the next vessel, it becomes the coolant for the second gas in the chain. When the next gas is pressurized and passes through the inner coil, it liquefies and is at an even lower temperature. The second liquid goes on to cool the next gas, and so on. Step by step, the liquefied gases become colder and colder. Each one is used to lower the temperature of the next gas sufficiently for it to liquefy. In the final stage, where hydrogen gas is cooled, the idea was to put it under enormous pressure, 180 times atmospheric pressure, and then suddenly release it through a valve. This would trigger a massive drop in temperature, sufficient to turn hydrogen gas into liquid hydrogen at minus 252 degrees, just 21 degrees above absolute zero.
Here was the risky bit, because his apparatus was going down in temperature, getting very, very cold, so very fragile, quite easy to fracture, while at the same time the pressures he was working at were very, very high, so the possibility of explosion. He took the most amazing risks, both with himself, he was a lion of a man in terms of courage, and with those around him. All the equipment he was working with could have crumbled or blown up, and more than occasionally it did.
Dewar had many explosions in his lab. Several times assistants lost their eyes as shards of glass catapulted through the air.
In the notebook, he actually jots down many details of what happened in the apparatus, but not what happened to his assistants. So somehow you get the impression that apparatus is more important than the assistants.
Well, the assistants seem to have been quite loyal to him because they stayed working. I mean, if you look at the picture of Dewar lecturing, there are two assistants there, one of whom has lost his eye, but the painter manages to portray him with his lost eye facing the other way, so you don't actually see it in the picture. So clearly there was something going for Dewar with his assistants in that they kept that sort of loyalty in a way that would be almost inconceivable in the modern world.
Over in Leiden, Onnes was facing anxious city officials who were so worried about the risk of explosions that they ordered the lab to be shut down. Dewar wrote a letter of protest on behalf of Onnes, but the Leiden lab remained closed for 2 years.
Well, Onnes had to wait and to wait and to wait. Dewar was already starting with liquefying hydrogen, and well, Onnes had the apparatus to do so too, but it just couldn't start, so we had lost the battle before it was even begun.
The year is 1898. Dewar has been working on trying to liquefy hydrogen for more than 20 years, and he's finally ready to make the final assault on Mount Hydrogen.
By using liquid oxygen, they brought down the temperature of the hydrogen gas to minus 200 degrees centigrade. They increased the pressure till the vessels were almost bursting, and then opened the last valve in the cascade.
Shortly after starting, the nozzle plugged, but it got free by good luck. And almost immediately drops of liquid began to fall, and soon accumulated 20 cubic centimeters.
Dewar had liquefied hydrogen, the last of the so-called permanent gases. To prove it, he took a small tube of liquid oxygen and plunged it into the new liquid. Instantly, the liquid oxygen froze solid. Now he was convinced. He had produced the coldest liquid on Earth and had come closer to absolute zero than anyone else.
Dewar thought that he had done the most amazing feat of science in the world, that he would be immediately celebrated for it and get whatever prizes there were available. And that didn't happen.
I think for Dewar, it was the ambition of a mountaineer. You've climbed the highest mountain peak that you can see in the range around you, and just as you get to the top of the peak, there's an even higher mountain just beyond.
That mountain was helium, a recently discovered inert gas. Van der Waals' theory predicted helium would liquefy at an even lower temperature than hydrogen, at around 5 degrees above absolute zero. Now all Dewar had to do was to obtain some. It should not have been difficult. The two chemists who had discovered the inert gases, Lord Rayleigh and William Ramsay, often worked together in the lab next door. Unfortunately, Dewar had made enemies of both of them by publicly criticizing their science and belittling their achievements, so they had no desire to share their helium.
Onnes was faced with the same problem as Dewar, which is, where can I get a supply of helium gas? And he actually asked Dewar to try and collaborate with him, too. And Dewar said, I'm having such a problem getting the gas by myself, I can't possibly give you any. I'd like to, but I can't.
Eventually, each found a supply. But Onnes's industrial approach paid dividends. After 3 years, he had amassed enough helium gas to begin experiments. The tortoise was beginning to pull away from the hare.
The liquefaction of these gases had become a matter of enormous pride and prestige for Dewar, but pretty quickly he ran out of resources. He was reaching the limit of what the budget would bear at the Royal Institution, and the helium supplies dried up.
One day, when they were in the midst of working with gaseous helium, an assistant in Dewar's lab turned a knob to the left instead of to the right. A whole canister of the gas escaped into the air, and they had 6 months when they couldn't do any work whatsoever. Dewar was furious.
At one point, Dewar writes to Onnes telling him that he's not in the race anymore. He thinks that the problems for liquefying helium are such that he's not able to complete the job.
The battlefields of science are the centers of a perpetual warfare in which there is no hope of a final victory. To serve in the scientific army, to have shown the initiative, is enough to satisfy the legitimate ambition of every earnest student of nature. Thank you.
In the summer of 1908, Onnes summoned his chief assistant, Flim, from across the river. They were finally ready to try to liquefy helium. At 5:45 on July the 10th, he assembled his team at the lab. They had rehearsed the drill many times before. Leiden was a small university town, and the word quickly spread that this was the big day. It took until lunchtime to make sure the apparatus was purged of the last traces of air. By 3 in the afternoon, work was so intense that when his wife arrived with lunch, he asked her to feed him so he didn't have to stop work. This was a man obsessed. At 6:30 in the evening, the temperature began to drop below that of liquid hydrogen.
It's getting very late in the day, and the team is down to its last bottle of hydrogen. If they can't liquefy helium now, they're going to have to wait for months to try again. And the temperature gauge is stuck at 5 degrees above absolute zero. And Onnes doesn't know why this is. And a colleague comes in, and he suggests that that means maybe they've actually succeeded and they don't even know it yet. So Onnes takes an electric lamp type thing, and he goes underneath the apparatus and looks, and sure enough, there in the vial is this liquid sitting there quietly. It's liquefied helium.
They had reached minus 268 degrees centigrade, just 5 degrees above absolute zero, and finally produced liquid helium. This monumental achievement eventually won Onnes the Nobel Prize. When James Dewar heard that he had lost the race to Kamerlingh Onnes, it reignited a festering resentment. Dewar berated his long-suffering assistant, Lennox, for failing to provide enough helium. Only this time, Lennox had had enough. He walked out of the Royal Institution, vowing never to return until Dewar was dead. And he kept his word. For Dewar, it was the end of his low-temperature research.
He must have been incredibly irritated, and knowing Dewar, he must, one can imagine that sort of irritation he would have felt when Onnes came in for the Dutch to liquefy helium. And even today, Onnes' discovery of liquid helium is seen as a much more significant discovery than Dewar's work on liquefying hydrogen, which is slightly unfair because it's all part of the process of trying to achieve absolute zero.
It remained, that's very clear, a wound in Dewar's soul that never really healed. I think that Dewar emerges at the end of this story as a rather tragic figure, one of the very greatest late 19th century British scientists who, in the end, is frustrated by a failure which hardly anybody could have expected him to achieve.
James Dewar's dream of reaching absolute zero was over. He spent the rest of his life investigating other scientific problems, such as the physics of soap bubbles. He had always been a loner. Ultimately, his refusal to collaborate cost him the glory he felt he deserved.
I think it's really impressive how often scientists do seem to be driven by the spirit of competition, by the spirit of getting there first. But what's really fascinating about these races, the race for absolute zero, is that the goalposts move as you're playing the game. The race in science is not for a predetermined end, and once you're there, the story's over, the curtain comes down. That's not at all what it's like. Rather, it turns out you find things you didn't expect. Nature is cunning, as Einstein would have said, and she is constantly posing a new challenge, unanticipated by those people who start out on the race.
Sometimes, an unexpected event triggers a whole new area of research. This happened in Leiden as Onnes's team began to investigate how materials conduct electricity at these very low temperatures. They observed that at around 4 degrees above absolute zero, all resistance to the flow of electricity abruptly vanished.
The electrical resistance dropped as if it had gone over a cliff. It was going down and down and down, and then it disappeared, or all but disappeared. And this was an astonishing thing. Nobody had ever seen anything like this before. There was nothing on Earth that had no electrical resistance.
Onnes later invented a new word to describe this bizarre phenomenon. He called it superconductivity.
We have a circular ring of permanent magnets which are producing a magnetic field. And now when we put a superconducting puck over it and give it a little push, the magnetic field repels the superconductor.
The magnetic field from the track induces a current in the supercooled puck, which in turn creates an opposite magnetic field that makes the puck levitate.
It produces a magnetic field like a North Pole against the North Pole, and that's why you have the repulsion.
As the puck warms up, its superconducting properties vanish along with its magnetically induced field. For decades after its discovery in 1911, the underlying cause of superconductivity remained a mystery.
Every major physicist, every major theoretical physicist had his own theory of superconductivity. Everybody tried to solve it, but it was unsuccessful.
There were more surprises ahead. In the 1930s, another strange phenomenon was observed at even lower temperatures. This rapidly evaporating liquid helium cools until at 2 degrees above absolute zero, a dramatic transformation takes place.
Suddenly, you see that the bubbling stops and that the surface of the liquid helium is completely still. The temperature is actually being lowered even further now, but nothing particular is happening. Well, this is really one of the great phenomena in 20th century physics.
The liquid helium had turned into a superfluid, which displays some really odd properties.
Here I have a beaker with an unglazed ceramic bottom of ultrafine porosity.
Ordinarily, this container with tiny pores can hold liquid helium. But the moment the helium turns superfluid, it leaks through.
We call this kind of flow a superflow.
Superfluid helium can do things we might have believed impossible. It appears to defy gravity. A thin film can climb walls and escape its container. This is because a superfluid has zero viscosity. It can even produce a frictionless fountain, one that never stops flowing. Superfluidity and superconductivity were baffling concepts for scientists. New radical theories were needed to explain them. In the 1920s, quantum theory was emerging as the best hope of understanding these strange phenomena. Its central idea was that atoms do not always behave like individual particles. Sometimes they merge together and behave like waves. They can even be particles and waves at the same time. This strange paradox was hard to accept, even for great minds like Albert Einstein. In 1925, a young Indian physicist, Satyendra Bose, sent Einstein a paper he had been unable to publish. Bose had attempted to apply the mathematics of how light particles behave to whole atoms. Einstein realized the importance of this concept and did some further calculations. He predicted that on reaching extremely low temperatures, just a hair above absolute zero, it might be possible to produce a new state of matter that followed quantum rules. It would not be a solid, or liquid, or gas. It was given a name almost as strange as its properties: a Bose-Einstein condensate. For the next 70 years, people could only dream about making such a condensate.
Matter can exist in various states. Atoms at high temperature always form gases. If you cool the gas, it becomes a liquid. If you cool the liquid, it becomes a solid. But under certain circumstances, if you cool atoms far enough to extremely low temperatures, they undergo a very strange transformation. They undergo an identity crisis. So let me show you what I mean by an identity crisis. When you go to low temperatures, the quantum mechanical properties of the atoms become important. These are very strange, very unfamiliar to us, but in fact, each one of these atoms starts to display wave-like properties. So instead of points like that, you have little wave packets like that moving around. It's really difficult for me to explain just why that is, but that's the way it is. Now, as you go to very low temperatures, the size of these packets gets longer and longer and longer. And then suddenly, if you get them cold enough, they start overlapping. And when they overlap, the system behaves not like individual particles, but particles which have lost their identity. They all think they're everywhere. This little wave packet over here can't tell whether it's this one or that one or that one or that one or that one or that. It's there and it's there and it's there. They're all in one great big quantum state. They're all overlapping. They're all doing the same thing. And what they're doing, to a good approximation, is they're simply sitting at rest. This Bose-Einstein condensate is very difficult to imagine or to visualize. I can imagine what it's like to be an atom running around gaily, freely, bouncing into things, sometimes going fast, sometimes going slow. But on the Bose condensate, I'm everywhere at once. I've lost my identity. I don't know who I am anymore. I'm at rest, and all the other atoms around at rest, but they're not other atoms around. We're all just one great big quantum system. There's nothing else like that in physics, and certainly not in human experience. So just to think about this causes me wonder and confusion.
Dan Kleppner's group at MIT began to try to make a Bose-Einstein condensate in hydrogen.
As we started out the search for Bose-Einstein condensation, our enthusiasm grew because hydrogen seemed like such a wonderful atom to use. It had everything going for it. It had its light mass. That means that the atoms will condense at a higher temperature than other atoms would. The atoms interact with each other very, very weakly. All the signals seem to be pointing to the fact that hydrogen was the atom for getting to Bose-Einstein condensation.
Dan Kleppner's idea was to cool the hydrogen atoms by making use of their magnetic poles. He used a strong magnetic field to create a cluster of atoms in a cold trap. Unfortunately, sometimes one atom flipped another, which triggered a release of energy that raised the temperature.
It was a frustrating time for us because our methods were so complicated. We were having a hard time moving forward.
It was time for the next generation to have a go. Two scientists who trained in Kleppner's department moved out west to Boulder, Colorado. They came up with a different approach to the problem. Rather than focusing on the lighter atoms of the periodic table, Eric Cornell and Carl Wyman hit upon the idea of using much heavier metallic atoms like rubidium and cesium. But would using these giants enable them to reach closer to absolute zero?
The idea in the field in those days was that the light things like hydrogen and lithium would be easier. And there were some good reasons for thinking that, but we had other ideas.
Yeah, sort of gut intuition in some sense.
Their plan was to use a laser beam to cool the atoms, a technique that had already been tried at their old lab at MIT. Lasers are usually associated with making things hot, but if they are tuned to the same frequency as atoms traveling at a particular speed, they can make them cold. When the stream of light particles from the laser hits the selected atoms in the gas cloud, the atoms slow down and hence become cold. Laser cooling was a new tool that had the potential to reduce the temperature of a gas to within a few millionths of a degree of absolute zero. But Cornell and Wyman were not the only ones excited by this prospect. A new scientist had arrived at MIT.
It was in late 91 or early 92 that we had an idea how a different arrangement of laser beams would be able to cool atoms to higher density. And it worked. And this was really a trigger point. I will never forget the excitement in those group meetings when we discussed what do we next. Because with higher density, there are many things you can do. Could we now push to Bose-Einstein condensation?
Quetelet used the full might of MIT's funding to build a laser lab to try to make a condensate in sodium atoms.
This is an atomic beam oven. What is wrapped in tin foil is a little vacuum chamber where we heat up metallic sodium so the metallic sodium melts and evaporates. And it's ultimately the sodium vapor, the sodium atoms, which we tried to Bose-Einstein condense.
MIT, Boulder, and several other labs were chasing the same goal. It had echoes of the race to produce liquid helium almost a century earlier.
As I tell my students today, anything worth doing is worth doing quickly, because science moves on, and we're all mortal, and you want to do things.
While MIT was installing expensive industrial lasers, Carl Wyman had a different approach.
Throughout my experimental physics career, I've always felt that technology played a big part. So if you could figure out a better technology for doing something, it was going to pay off in the long run in physics.
In some cases, he was ripping open old fax machines and taking out the little chip inside that made the laser, and showed that you could take these lasers and put them into a home-built piece of apparatus, stabilize the laser, and use them to do spectroscopy and laser cooling.
This is actually our first, what's called the vapor cell optical trap. You can see it's kind of this old cruddy thing, pulled together glass, where we could send laser beams in from all the different directions and have just a little bit of the atoms we wanted to cool.
As well as bombarding the atoms with lasers, they also trapped them in a strong magnetic field.
You could have all your magnetic trap coils outside the vacuum system. It's, again, just a lot easier, simpler to do everything.
We would try this sort of magnetic trap, that sort of magnetic trap, this sort of imaging, that sort of imaging, that sort of cooling. All those things we could do without building a whole new chamber each time. We tried literally 4 different magnetic traps in 4 years, instead of having a 3 or 4 year construction project for each one.
By being fast and flexible, the Boulder group hoped to beat their old lab at MIT. But MIT had its own plans. This was a prize they felt should be theirs.
There was a sense of competition, but it was what I would call friendly competition. I mean, can you imagine 2 athletes? They are in the same training camps, they help each other, they even give tips to each other. But then, when it comes to the race, everybody wants to be the first.
The rival groups were all using magnetic trapping and laser cooling to cool their atoms. But for the final push towards absolute zero to turn these atoms of gas into the quantum state Einstein had predicted, they needed one more cooling technique: evaporative cooling.
It's just like with this coffee. The steam coming off the coffee is the hottest of the coffee molecules escaping and carrying away more than their fair share of energy. In the case of the atoms, we keep the atoms in a sort of magnetic bowl, and we confine the atoms there. They zoom around inside the bowl, and then the hottest ones have enough energy to roll up the side of the bowl and fall over the edge, slop over the edge, taking away with them much more than their fair share of energy, and the atoms that remain have less and less energy, which means they move slower and slower and start to cluster near the bottom. And as that happens, we gradually lower the edges of the magnetic trap, and always, so there's just a few atoms that can escape, until finally the remaining atoms cluster near the bottom of the bowl, huddled together. They get colder and colder and denser, and eventually in this way evaporation forces the Bose-Einstein condensation to occur. One problem that we kept encountering is that we had to keep the atoms isolated from the walls. We had to have a really good vacuum. And yet, if the vacuum is perfect, what is it that you're actually working with? We had to have a little bit of rubidium gas in there, a tiny bit of rubidium gas that we could catch with our lasers and slow down. So we had this wild idea of constantly changing the pressure in the chamber, letting the pressure get higher and lower, and we built a very elaborate chamber with valves that opened and closed and pumps that turned on and off, and it didn't work for beans. I mean, we spent 6 months wasted, I might say, 6 months on valves opening, closing, pumps turning on and off. The problem is the rubidium gas has a little bit of stickiness to it, and that meant while we were trying to get all the rubidium out of there, that residual gas was heating up the atoms. So eventually, we had to give up on that idea.
By now, the race to produce a Bose-Einstein condensate was intensifying.
At every major meeting, Eric Cornell and I gave talks or talked to each other. We were keenly aware that we were both working towards the same goal.
It's a mixed thing. On the one hand, it's flattering because they're using an approach which we had pioneered and we felt good about that. On the other hand, it made us a little nervous because we want to advance knowledge, but science is a competitive business, and we felt that we wanted to do it first, and maybe that we were entitled to do it first. Although even that's a mixed bag, because after all, we had jumped into the game of the hydrogen people who had shown us so many of the tricks over the years.
At one point during that period, I remember Carl Wyman being quoted in an article saying that he hopes that the MIT group gets there first because they started it all, and so they would get the Nobel Prize, and then the Gilla group could do all the interesting science. Well, that was a very nice thought. It didn't quite work out that way.
In June 1995, the Boulder Group was working round the clock, knowing that several other labs were also poised to produce the first condensate. An official visit from a government funding committee was the last thing they needed.
The standard thing you do when the important people come around is you close down your lab and clean up everything and put posters on the walls so they can see how productive you are. Of course, that's the exact opposite of being productive. We didn't want to close down the lab or clean up our lab or put up posters. We wanted to work very hard. So the senior dignitaries in the three-piece suits and so on came in to the lab, and we left the lights off, and everyone continued to work. And I made them keep their voices down and talked to them rather in a hurried way, and then sort of shuffled them out the door. And they all had a slightly puzzled look on their face, because it probably had never happened to them before in the history of being a visiting committee, that they were treated with as little pomp. And later I actually met one of the guys who said, I suspected something was up that day, because otherwise you never would have dared to do that.
June the 5th, 1995, turned out to be a big day in the history of physics. They had finally made what Einstein had predicted 70 years before, a Bose-Einstein condensate.
Our first reaction was, wait, we got to be careful here. Let's think of all the different knobs we can turn, checks we can make, and so on, to see if this really is Bose-Einstein condensation.
condensate is sort of like a vampire. If the sunlight even once falls on it, it's dead. And so its realm is the realm of the dark. But we can take pictures of them because we strobe the laser light really fast, and even as the condensate's dying, it casts a shadow, and the shadow is frozen in the film.
Wyman and Cornell created the first Bose-Einstein condensate in a cloud of just 3,000 atoms of rubidium, the first in the universe, as far as we know. They had reached a temperature of 170 billionth of a degree above absolute zero.
One of the first things you need to understand about Bose-Einstein condensation is how very, very cold it is. Where we live at room temperature is far above absolute zero on this scale. Imagine that room temperature is represented by London, thousands of kilometers from here. Then on that scale, if we imagine right here where I'm standing in Boulder is absolute zero, the coldest possible temperature, then how close are we to absolute zero? If we think of London as being room temperature and right where I am is absolute zero, then Bose-Einstein condensation occurs just the thickness of this pencil lead away from absolute zero.
Within weeks of the Boulder Group's success, Wolfgang Ketterle produced an even larger condensate from 10 million sodium atoms. At last, quantum mechanics was more than just theoretical mumbo-jumbo. It was something that could be seen with the naked eye. Wyman, Cornell, and Ketterle shared the Nobel Prize for Physics in 2001.
One of the things the Nobel Prize means, and the ceremony means, that everybody remembers Eric's the person who forgot to bow to the king.
There was a breakdown of protocol on my part. There was no excuse because they actually drill us. It's more like you have a series of rehearsals practicing how to bow to the king, and I somehow managed to bollocks it up at the last possible moment. And I thought maybe, Carl, who came after me, would make the same mistake, and then no one would figure it out. But no, he was perfect.
I heard about the Nobel Prize when I was woken up by a telephone call, which was at, I think, 5:30 in the morning. So you wake up, you go to the telephone, and somebody tells you, congratulations, you've won the Nobel Prize. You're still tired, your brain is not fully functional, but you realize this is big, and what you feel is pride for MIT, your collaborators, for yourself. It's wonderful to see that your work gets recognized and acknowledged in this way.
Like any great adventure, the pursuit of science offers no guarantee of success. But for the godfather of ultra-cold atoms, persistence eventually paid off. After 20 years of struggling to obtain a condensate in hydrogen, Dan Kleppner finally succeeded. For a few fleeting moments, his dream came true.
Of course, we were delighted, and I think everyone was delighted, because we'd been working on it for so long. It's kind of embarrassing to have this group which helped start the work and was working away there fruitlessly while everyone was enjoying success. When we got it, everyone was happy.
To see that an effort which lasted for 20 years, which took so much patience, frustration, and tenacity, to see that succeed is just emotional, it's liberating. I will never forget this standing ovation which Dan Kleppner received at the Varenna Summer School when he announced Bose-Einstein condensation in hydrogen.
Everybody just got up and it was sort of like an opera where everybody just cheered and people were crying, and because everybody realized that they had finished the race, but too late, and it wasn't going to work out, but in some sense they had really stimulated the whole field, so it was a very moving moment.
For the pioneers who had realized Einstein's dream and created condensates, it was the end of an extraordinary decade of physics. Now there was a new challenge: to work out what to do with them. At Harvard, a Danish scientist, Lena Howe, had the idea of using a condensate to slow down light.
We all have this sense, light is something that nothing goes faster than light in vacuum. And if somehow we could use this system to get light down to, to a human level, I thought that was just absolutely fascinating. It is actually very odd. It's also extremely odd to a lot of my colleagues.
Lena Howe created a cigar-shaped Bose-Einstein condensate to carry out her experiment. She fired a light pulse into the cloud. The speed of light is around 1 billion kilometers per hour, but when the pulse hits the condensate, it slows down to the speed of a bicycle.
So light pulse might start out being 1 to 2 miles long in free space. It goes into our medium, and since the front edge enters first, that will slow down. The back edge is still in free space. That'll catch up, and that'll create that compression, and it'll end up being compressed from 1 to 2 miles down to 0.001 micron, or even smaller than that. You could say, well, gee, it's easy to stop light because I could just set a laser beam into a wall and I would stop it. Well, the problem is you lose the information because it turns into heat. You can never get that information back. In our case, when we stop it, the information is not lost because that's stored in the medium. And then when we have time to revive it, the system has all the information to revive the light pulse and it can move on.
One day, ultra-cold atoms will probably be used to process information, but quite how is hard to predict. Sometimes the promised benefits from a scientific breakthrough take a long time to emerge. Many predicted that by this century, energy-saving superconducting power lines and maglev bullet trains would be crisscrossing the continents. Perhaps now, as world energy supplies dwindle, these technologies, once seen as uneconomic, will start to take off. Now it is the quantum nature of the cold frontier that has captured imaginations. Supercooled quantum devices are mapping the magnetic activity of the brain. And cold atoms are being turned into quantum computers.
As a quantum mechanic, I engineer atoms. To make a computer out of atoms, you have to somehow get atoms to register information and then to process it. Why build quantum computers? Because they're cool, it's fun, and we can do it, right? I mean, we actually can take atoms, and if we ask them nicely, they'll compute. That's a lot of fun. I mean, have you ever talked to an atom recently and had it talk back? It's great, learn to speak atom and the atom speak back, that's great. So the first thing we're going to do is we're going to set up. The quantum world is, and the world of the very small, it's like an exotic wilderness that you've never been in before. Things you wander in, and everything looks strange, and you see things that you've never seen. But if you really want to see what's going on, then you've got to be quiet. So if you go into the wilderness and you're going, blah, 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 then you're never going to see things because all these exotic phenomena are going to know that you're there and they're going to stay put and they're not going to come out. So if you make a lot of noise, that's bad. Now, at the quantum level, at the microscopic level, heat is noise. So if you want to see these strange and exotic effects, you have to be quiet, very quiet. There can't be a lot of noise, and that means you have to cool things down. Yes, look at that, that's beautiful.
Unlike ordinary computers, where each decision is based around a bit of information and is either a 0 or a 1, in the quantum world, the rules change.
At first glance, a quantum computer looks almost exactly the same. But quantum mechanics is weird. It's funky, okay? It's weird.
When you do quantum computing, you want to make this weirdness work for you.
So now let's look at our quantum bit, or qubit.
The qubit can not only be a 0 or a 1, it can also both be a
0 and 1 at the same time. It's almost like a form of
And if you
parallel
look at the many
computation.
worlds
But in a parallel
interpretation of
computer,
a quantum
one
computer,
processor does this, one
what
processor
happens
does that.
is
So you have
that
two processors
your
doing this and that.
quantum
In a
computer
quantum
is
computer, you
doing
have only
many,
one
many
processor
computations
that's
all
doing
at the
this
same time.
and that at the same time.
Looks like it's more the tuning. So
Within the giant Dewar flask lies a prototype quantum computer surrounded by its supercooled, superconducting magnet. In the future, quantum computing could be used to predict quantum interactions, such as how a new drug acts on faulty biochemistry, or to solve complex encryption problems, like decoding prime numbers that are the key to internet credit card security. This weird quantum world is part of a new frontier opened up by the descent towards absolute zero. It's been a remarkable journey for scientists into unknown territories far beyond the narrow confines of Earth. On the Kelvin temperature scale, which begins at 0 degrees for absolute zero, the temperature of the Sun is around 5,000 degrees. At 1,000 degrees, metals melt. At 300 degrees, we reach what we think of as room temperature. Air liquefies at 100 degrees. Hydrogen at 20 degrees. Helium at 4 degrees. The deepest outer space is 3 degrees above absolute zero, the coldest place outside the laboratory. But the descent doesn't stop there. With ultra-cold refrigerators, the decimal point shifts 3 places to a few thousandths of a degree. And laser cooling takes it down 3 more places to a millionth of a degree, the temperature of a Bose-Einstein condensate. With magnetic cooling, we shift 4 more decimal places until we reach the coldest recorded temperature in the universe at a lab in Helsinki, 100 pico-Kelvin, or a 1/10 of a billionth of a degree above absolute zero. So will it ever be possible to go all the way, to reach the holy grail of cold, 0 degrees?
Getting to absolute zero is tough. Nobody's actually been there at absolute 0.000000 with an infinite number of zeros. That last little tiny bit of heat becomes harder and harder to get out. And in particular, the timescales for getting it out get longer and longer and longer, the smaller and smaller the amounts of energy involved. So eventually, if you're talking about extracting an amount of energy that's sufficiently small, it would indeed take the age of the universe to do it. Also, you actually need an apparatus the size of the universe to do it, but that's another story.
Absolute zero may be unreachable, but by exploring further and further towards this ultimate destination of cold, many fundamental secrets of matter have been revealed. If our past was defined by our mastery of heat, perhaps our future lies in the continuing conquest of cold.
On Thursday at 9 on BBC4, our Science You Can't See series continues with that tiniest of keys to the biggest of questions, the atom. The Marley Brothers are jamming live at Glastonbury next.